Okay, we'll go with that. So yeah, I'm here to talk a little bit about stratospheric exploration. I've been a pilot for 30 years. I fly all kinds of helicopters and planes and other kinds of things. But if you have any questions about all of that, I'm happy to do it. But this is about stratospheric exploration, and stratosphere is a really interesting place. It's beautiful. This was taken from the International Space Station, but it gives you a kind of a view of what the Earth looks like from up high. Beautiful clouds, very thin atmosphere, darkness of space, above it. It's a place that's rarely visited. The rockets go right through it in a heartbeat, and they're fireball come back through it. But it's a beautiful spot, and someplace that I felt like deserved more attention. Um, Most people, like I said, do this with rockets, but I wanted to explore something a little different, which is scuba diving. So, what would it look like to scuba dive in the stratosphere? So you had everything with you. You have all the oxygen that you need. You've got a balloon. You're up high, um, and you can actually enjoy it. Silently and beautifully. You can enjoy the beautiful environment that you have around you. And I think from my skydiving experience, I've always wanted to go higher and higher. And this is, about as high as any human. It is higher than any human has ever gone with the intention of skydiving out of. And so if you take the scuba diving analogy and you say, well, what would a scuba diving outfit look like with the stratosphere? Um, it would be quite different. And behind me is actually that suit that we use to do it. But I also want to talk a little bit about my family at the time of the jump, because as cool as stratospheric exploration seemed to me, my family was super worried about it and super worried about me. So don't forget, is anytime you try to do something which is outside the boundaries of what's reasonable, there's other impacts you have on your family at the same time. So this is what scuba diving for the stratosphere looks like. It's a pressure suit. This is almost an identical suit that they use for extra vehicle activity, and that you see on the International Space Station. So if you go out in space, you need a suit like this. And matter of fact, it's probably made by the same company that made this suit, ILC Dover. You need a parachute. In my case, two parachutes, main and reserve parachute. So if one fails, then you had one more chance. And parachutes don't fail that often, so it gives you a lot of redundancy. You need oxygen because essentially you're above 99.9% of the atmosphere. So you need that. You need a heater because it gets pretty cold up there, especially on the way up. And the reason you need a spacesuit is because, as the pressure goes down, the boiling point of water goes down. So the higher you get, the lower the boiling point. You guys probably know this from, if you go up to Lake Tahoe and boil water, it boils at a much lower temperature. So it takes a long time for your spaghetti to boil up there because it's boiling at a lower temperature. Well, it takes less time for it to boil, but it takes longer time to cook because the water temperature is actually much lower. So if you go high enough, your 98.6 degree blood is going to reach a point where the atmosphere is thin enough so that it will boil. That point is called the Armstrong line, and it's about 66,000 feet. So what you need to do is artificially create some pressure around your body so that because with increased pressure, it basically makes it so you don't have to worry about the boiling point as much. And so anyways, that's what the spacesuit does. So that's the suit that we use, and that's actually me in the suit. Before you can get up to space, you have to test the suit and the parachute and deployment systems at lower altitude. So this is a video that we shot. This is the last airplane test that we did. So everything is exactly the same as it will be for the balloon, except rather than being released from a balloon, I'm going to roll out on rollerblades out the back of an airplane, as you'll see right now. So this test was probably from around 17,000 feet or something like that. It was the last test we did out of an airplane, and it's to make sure that I have control over my turns in both directions, make sure that I can pull my own parachute, make sure that I actually tried several different ways of turning during this. You see me kind of bobbling up and down. That's a side effect of the drogue parachute that you see, coming from my back. The key to making to not spinning is a drogue parachute that's high on your back. And so now you see me pulling. We reach down, grab the handle, pull as hard as I can. Parachute comes out, and my two safety divers. There's actually three safety divers. They're not fun. They're not finished having fun. They take off. This is over Roswell, New Mexico. So that was one of the tests. Once you finish the airplane test, then you can try it on balloon. I did 3 balloon flights. This is the middle one. You see a lot of the elements of a balloon system. You see the balloon, the helium that's in the balloon is actually only in the top part of the balloon. Then there's this long tail. Behind it, you see a truck. That's the helium truck. And you can see a couple other balloons up there. Those are aerostats that are trying to tell me what the wind is like up there and tell the meteorologist what the wind is like. So as this balloon's going to ascend, that long tail is actually going to get filled with helium. And the reason is, as the balloon goes up, the pressure of the outside air goes down, and therefore that balloon has to expand. And believe it or not, when you get to the very top, that balloon will be completely round. It'll be gigantic and round, and it will be huge at that point. The final balloon that you'll see in the next video was a balloon that you could fit any professional football or baseball stadium inside of. That's how big the balloon was. This is slightly smaller. This was the balloon that we used to go up to 105,000 feet. So once you see the balloon is standing straight up here, then you'll see the spool open. That tractor will back up. And now you see the 2 straps that are holding the balloon down. We can tell exactly how much what's called free lift. So how much will this balloon lift up? We can tell exactly whether it's leaning over, whether the wind is bad, whether it's gusty, all these kinds of things. And at that point, when everybody believes it's safe for me to be underneath this balloon, then you'll see me enter stage right here, and you'll see this little dolly that is dragging me in, and they put me underneath the balloon, and then they hook up 2 connections, and then I'm gone. And you'll see that in the next video. So this is the next video. It's in Roswell, New Mexico. It's the middle of the night. The process starts about midnight. The launch of the balloon happens around dawn. This is what it looks like. There's the helium truck again. The mission control is the middle building. They're putting the suit on. It takes about an hour and a half to put on the suit. You have to pre-breathe oxygen because otherwise you need to get the nitrogen out of your system. Otherwise you can get decompression sickness. Once all that's done, they take me out to the launch area. There's a little train behind me, has oxygen and consumables that I need for the trip out there. Those will be disconnected. Now you see the full balloon, giant balloon, and that's the balloon that'll take me up to 135,890 feet. You can see the release is about to happen here. And you go, essentially straight up there. It's about 2 hours and 7 minutes to get to, the final altitude of 135,890 feet. It's the most gentle, beautiful, trip you've ever taken. It's very quiet. You're constantly turning slowly in the balloon, so you get a view in all directions. Balloon basically went pretty much straight up for the first 10,000 feet, and then it started drifting to the south, and later on it drifted, very fast to the east. People think the jet stream is where all the winds are, and there are winds in the jet stream, but in this day, that jet stream actually had pretty mild winds. But if you get up high enough, you get to something called stratospheric winds, which, at my altitude were, about 120 miles an hour, which is super fast. It's so fast that the helicopters have trouble keeping up. This is a control room here. My sisters, 2 of my sisters are there. This is what it looks like kind of up at, high altitude. It's really pretty. There's a shot here that I think gives you kind of a best view of what it looks like. The Earth isn't that curved. This is kind of a lens effect, but it does show you the layers of the atmosphere pretty well, which I think is really pretty. Um, and this is the view I think that's kind of closest to what it looks like at 135,000 feet. It's right before I launched, or right before I was dropped. Um, you'll see me move my legs. That's how I signal to the ground area. They had a downward facing camera. There's my mission control director right there, and he's counting down, 5, 4, 3, 2, 1, and then I'm about to release. There's a release. There's a drogue parachute that comes out, really clever thing. You'll see me do a backflip here, and you'll get a good view of what the balloon looked like. See, it's giant and round there. It doesn't have the tail anymore. You also see a drogue parachute hanging down below me. Uh, uh, you'll see the balloon go by again as I started going down. It took 4 minutes and 27 seconds to before I pulled the parachute, and during that time, the top speed was around 822 miles an hour, which is Mach 1.2. Crossing the speed of the sound, there was nothing that would tell me when I crossed the speed of sound. But on the ground, they did hear a sonic boom, which was kind of cool. So anyway, we're going to fast forward here because 4 minutes and 27 seconds is a long time. And we'll get to opening. That's Mark Kelly. He's now Senator, U.S. Senator. So I get down low, I pull the parachute, came out beautifully. You can see this picture was taken above me. It was actually taken by a friend of mine who jumped out right after me, not at the high altitude, but as soon as I opened, he was in a plane that just crossed over, and he jumped out next to me, and he was my wingman on the way down, making sure that I didn't run into anything. This is the landing, or more appropriately, the crash. This suit plus me weighs like 270 pounds. I can't even stand up in it. So we're not going to have a gentle landing, but I was never hurt in any of the landings. You're landing in a giant airbag. That's my friend Blicky's coming over, and that's the thumbs up. We got all kinds of vegetation all over me, but it was all good. This is when the team hears that I'm down on the ground safely. So super excited about that. Anyway, so we can skip past that part. I'm gonna go back to this one section because I think it's just kind of cool. One of the hardest problems is maintaining stability when you're falling, and more particularly, how do you get a? I decided to have a drogue parachute. Red Bull didn't. Felix was in an inverted flat spin, really dangerous condition, and I wanted to avoid that. So we tried to figure out a way to make it spin less. And the secret is a drogue parachute, but it's not just a drogue parachute. You have to get the drogue parachute out at the right time. If you get the drogue parachute out too early, it can tangle around your neck and cause you going to spin. That happened to Joe Kittinger in 1959. If you get it out too late, you're going so fast that the drogue parachute will just explode. And so you need something kind of in the middle. And we came up with this idea, which is basically a roll of carbon fiber where the drogue bridle actually goes through the middle. So you'll see that happening in slow motion here. As I fall away, a roll of material turns into a pipe as I fall away. So you can see it rolling off the spool, but you see what comes out is actually a pipe. And it's a really cool thing. And then at the end of that pipe is another bridle with a drogue parachute. So what that makes it is it doesn't matter how much I spin, I can never get tangled up in that drogue parachute. And the other really nice thing is when the drogue starts working, it's going to pull at the end of that pipe. And as it pulls up on the end of that pipe, it's going to rewrite me. So I was actually back face to earth with the drogue working in 17 seconds. So it was very quick that drogue parachute was effective. It was as effective as early as it was humanly possible. And I stayed safe the whole time, which was like a wonderful piece of engineering, which had, super nice implications on the safety of the whole program. This is part of the team. This is the team that was actually available at Roswell the day of the final jump. It includes the Roswell Fire Department and a bunch of other people that are kind of hanging on. But anyway, there's a lot of people outside this picture that contributed to the project in one way or the other. So anyway, with that, I'll stop the screen sharing piece here. And and go back to the zoom if I can here, and get rid of all this, get rid of all this, and stop sharing. And I can talk to you. I can answer any questions you guys have about it. Hang on just a second. Get rid of all these windows in the way. Okay.
All right, awesome. Let's give him one more big round of applause for that. Thank you so much. All right, so let's start off with any questions anyone has. Go for it.
So in your suit, you mentioned you have an atmosphere that keeps you pressurized and allows you to breathe and survive. I know in certain missions or certain space missions, they had like a pure oxygen environment, and others it was sort of more like the atmospheric composition. In your case, what was sort of the composition of the sort of air in your suit?
Yeah, so in my case, it was 100% oxygen, with a little bit of a caveat. So one of the problems with these suit architectures, how do you define, is that the oxygen part is the easy part. So you get oxygen in. You really need close to 100% oxygen in this environment, because you're pressurized to low pressure, and therefore the amount of oxygen that you're actually getting. If you took normal things and then you reduce the pressure as much as we're reducing the pressure, you'd only get a certain amount of oxygen out of the air. And so you actually, I think these EVAs are all probably done with 100% oxygen. In my case, 100% oxygen. But the story doesn't end there about what happens to the oxygen, because you also have to worry about this other thing called CO2 and also moisture. So what happens to those? How do you get rid of those? And the way that the astronauts do it is they just blow so much oxygen by your nose and mouth that and it's vented out the suit. I mean, it's kind of, let me back up and say, how do you pressurize a suit? How's that actually happen? Because I kind of got the impression it was kind of like a balloon that you like blow up. You put it on a bottle and then you hit the thing and it blows up, and that's what happens to the suit. But it's not really that way. What you have is this thing called a dual suit controller, which is just a piece of electronics, which when you open it up has several settings on it. But what really happens is when you're on the ground, that setting is open, that valve is open. So anything that you breathe basically just goes right out of the suit. Suit stays flaccid, no big deal. But when you want to pressurize it, you close that valve. And so now what happens is you breathe in oxygen, and as you exhale, you blow up the suit. So you actually are blowing up this balloon, which is a suit, from the inside the whole way. So, and it doesn't take that long. It only takes a couple of minutes for you to blow out enough oxygen to actually completely blow up this balloon, which is a spacesuit that you're inside. And at that point, it's at the max pressure that suit is designed to hold. In my case, 5.4 pounds per square inch psi, which you don't think is very much. 5 pounds, no big deal. But if you look at how many square inches are on the inside of that suit, it's thousands of it. So 5.4 times thousands, you get a lot of pressure. So that suit's super strong. But what happens when you reach it? So I'm about to breathe out again, and that's going to blow up that balloon even more, but that balloon isn't going to blow up. So what happens? Well, the dual suit controller is this magical thing, and it senses the fact that we now have the maximum amount of pressure inside that suit is designed to handle. And so when you breathe out that time, it vents that breath. When you breathe out, it's going to vent it to the outside. And so that's how you keep 5.4 PS all the time, is you blow the thing up from inside, and then once the pressure is about to get too high, that valve opens, and it only opens enough to get it back down to 5.4 PSI. So that's how that works. But then you have to worry this problem about CO2. Like CO2, I don't have enough oxygen to I need like 5 hours of oxygen. And for that, I don't have enough oxygen to basically blow an unlimited amount of oxygen through by my nose and mouth. So I need to do something with that CO2, because CO2, even in small quantities, is actually lethal. And so, so you have to do something with it. So the trick to make that work in this suit architecture is when I breathe it out, I'm wearing an oxygen mask. And the oxygen mask isn't oxygen, you know, it looks like an oxygen mask, but that oxygen actually just comes from the outside environment. That's all oxygen around me. What it does is it vents my breathing out through a little, what looks like an oxygen tube actually, and it vents it out to the lower half of the suit. And then they put this rubber collar around the neck, which keeps the stuff that I just put in the bottom half of the suit from coming back up to the top half of the suit. Um, so that's how that system works. So I have 100% oxygen on the top above this thing. I have 100% oxygen mixed with carbon dioxide and moisture on the bottom half of the suit from the neck down, and then everything gets vented out, to the atmosphere, to keep the suit at a certain pressure. But it's 100% oxygen, and 100% oxygen is really flammable. So the number of things that we are allowed to have with me, like the only thing I'm allowed in that thing, I only have two things that actually run on electricity inside that environment. First is the microphone and the speakers for the headset. So I have that, and that's been proven through many years. It uses low voltage, other kinds of stuff to make sure that it doesn't spark anything or cause a fire. And then the second thing I have is a heart monitor and respiration monitor around my chest that's used to just record, that kind of information, and also has been tested, extensively before I put it on. So, but to answer your basic question, it's 100% oxygen environment.
Awesome. Thank you.
All right. Do we have? Yeah, Kyle, go ahead.
So like, as you were falling and getting faster, I noticed your head was shaking pretty violently, like near the end. So like, how did you not get hurt, and what did that feel like?
Yeah, it's this going up and down, that thing. That was a side effect of the spin resistant thing. So that drogue, we did a lot of tests. We thought just putting a drogue parachute in the normal place that you would for a tandem skydive would actually eliminate spins. It would certainly make you go face to earth. That was guaranteed. But the question is, would you spin? And what we learned through our testing process is that if we had put it in the normal place, we would have spun at 180 RPM, which is, definitely lethal. So we actually talked to a lot of people, including the Red Bull team, actually, about how they did their spin resistance. And they taught us something which is the connection point between the spin resistance system, between that bridle and skydiver, is super important. So moving it a foot up from the middle of your butt, basically down to the top of your neck, basically eliminates spins completely. So by moving that up, that got rid of the spins. Matter of fact, the spin rate, should have been over 180. I mean, we tested this at 120,000 feet, and the spin rate was over 100 RPM. I think actually it was 186 RPM, and that was nowhere near the final velocity we would have gotten on the record attempt, but certainly fatal. And when we moved the thing after all these tests that we did and stuff like that, I think the spin rate went from a higher altitude, went down to, I don't know, like 10 RPM or something like that. And it was nice is because it's so close to your head, when you spin, it's like a skater that's spinning in place. That's no problem. They can spin at very high RPM because their head is almost perfectly aligned with the axis of rotation. And by putting that attachment point right behind my neck, that essentially did the same thing. So not only was the spin a lot less, but the chance of getting hurt was a lot less. And so that's what caused that. But there was this horrible side effect of it. But actually, it might not even be a side effect. It may be actually part of the reason it doesn't spin is because it introduces this oscillation at about 0.8 hertz. So 0.8 times a second, you're going to go up and then down, up and then down. And, it's kind of like it's very disconcerting the first time you feel it, but the truth is it's not that bad. It's, think of it as, if you're on a rocking chair and somebody's just going up and down at about this speed, it's like, that's what happens. And it's not worse than a rocking chair, honestly. It's about that speed. So if you're trying to do your homework or something like that, and somebody's going up like this, down, it's probably pretty hard to do. But you get used to it. And so it wasn't actually a big deal. I didn't even think about it. My head wasn't really, I mean, it might seem like it was bopping up and down, but it wasn't really that big deal. I was just relaxing, honestly, and thinking about other things. And my head can't really go too far forward because the oxygen mask runs into the acrylic. I can't go too far back because there's not enough room because I'm wearing a helmet in addition to the oxygen mask. So anyway, I think that's one of those things that just looks worse than it is. It wasn't that big a deal.
All right. Yeah, Amit?
I'm not sure if you did mention it earlier, but you talked about how like the stratospheric winds were like up to like 120 miles per hour. How high was like the chance of you getting like blown way off course by that? Because like you said that it wasn't totally easy to predict, but I'm not sure if you said whether or not you could easily capture that. I don't know.
Yeah, it's a great question. Really good question. So these stratospheric winds are interesting. They actually change twice a year. Actually 4 times a year they change, and they go the opposite direction. It happens like in a day. Like the winds are blowing, stratospheric winds are blowing 120 miles an hour in one direction, and then the next day they're blowing 120, and they'll keep doing that for another 3 months, and then they'll switch again. It's the craziest thing because there's not that much mass up there. There's not that many particles, right? But the particles are moving really fast. So how do you predict where you're going to land? Because it's a balloon, right? So, but the stratospheric winds are pretty consistent in the sense that they're for that period of time, for that 3-month period, they always blow in the same direction. And then the next 3-month period, they'll blow in the other direction. And there's a transition period where they go really slowly. So what you do is we want to know where we're going to land, and we want to know the track that we're going to land. So what you do is the United States government, thankfully, launches these balloons, radiosondes, that basically go up and they track. They launch them in like 300 places in the United States, and they track what the winds are at every level. So at 1,000 feet, the winds are from this direction at this speed, and saying so. And they don't change so much day to day. So the days before, you're looking at the meteorology really well because you need to find a calm day to launch a big balloon. So we're already looking at the meteorology weeks, months ahead to find a window at which we think the launch winds are going to be so slow. Thing. I mean, we can take up to about a 5-mile-an-hour wind, but we have a meteorologist, a guy named Don Day, who can predict when we're going to have calm winds on the surface. And not just on the surface, it has to go up to like 600-700 feet because that's the height of the balloon. And so, but then the other thing that Don does for us is he basically uses a computer program, which is actually a pretty trivial computer program, that based on the fact that you're blowing this direction for this amount of time and this direction for this amount of time, and this thing, it can actually get a track along the ground of where you're predicted to go. And that's pretty darn accurate. And so the day before the launch, what we do is we take that prediction and we actually lay it out in Google Earth on exactly where we go. And then we get in a helicopter and we actually fly that entire path. And just to make sure it's like which areas are going to be best to land, which ones are going to be worse to land, are there any particular hazards we want to worry about? And the nice thing, the reason we launched in New Mexico, in Roswell, is everything in the east is landable terrain. I mean, there's one 200-foot cliff. There's no houses. There's practically no houses, practically no trees. There's almost no lakes. I mean, it's the most beautiful place in the world, to land. So that's what we do is to fly that, make sure we get that. And then about midnight before the real launch, we launch another aerostat, which goes all the way up, and it updates all those values to give us a very, very good production. And then we actually do it one more time right before launch, like 2 hours before launch. And because those predictions are so accurate, I land, even though there was 120-mile-an-hour wind, I landed with 70 miles in that way from the launch site within 1 mile of where we predicted. So those models are super accurate. They have really good data. So that's what you have to do. You have to predict where you're going to land, and then you have to position all your assets like trucks and airplanes and helicopters and all that to make sure that somebody can get to you at every point in that whole thing. And so that's what I did. But since we ended up going the full duration, and because we knew where we were going to land, and because I landed pretty much exactly where I was, we had all the assets were, including the trucks, were actually there when I landed. So it worked out really well. Great team timing and kind of a good use of computation.
Awesome. All right. All right. Okay. I think we can start this again. All right. Next question.
Were there any concerns about temperature, or did sort of the paint of the suit sort of deal with that?
No, it's a really good question. You guys are asking great questions. So yeah, the temperature gets down to like minus 120 degrees Fahrenheit. So it's colder than you would ever expect. And so we actually did a lot of tests to try to understand how the suit would behave. I had a kind of a long underwear underneath me that had little channels of small tubing that basically ran water that was heated, by the environmental system on the front, and that would mostly keep me, pretty warm. Hands were tough because you can't actually use that capillary system for your hands. So I had heated gloves, which kind of worked to a certain extent. And so we ran some tests where he basically put me in a refrigerator that was cooled by, a giant refrigerator that was cooled by liquid nitrogen, so they could set the temperature anywhere they wanted. And those tests were super freezing, and I actually had to run that test 4 times to get so I could safely deal with the cold. And we learned a lot in that. But in the actual test, it turned out, not to be that much of a big deal. Matter of fact, I think I turned off the heater at 70,000 feet and never had it again. So in the coldest parts of the ascent, I never had a problem with temperature. And you say, well, why? It was so cold up there. And I think in hindsight, it was kind of obvious that if you think about it from a molecular level, cold just means the molecules are moving really slowly, right? That's what cold temperature is. It's molecules moving really slowly. And the way that cold gets you is by conducting to you, which is really warm. And therefore it slows down the molecules in your body. But if you're at 130,000 feet, those molecules are, there's so few molecules that they're so far apart that conduction actually isn't a big deal. You don't actually conduct any heat away from you. And so if we had used a thermal vacuum chamber, we would have realized that, because all we had the money for was to do a thermal chamber. We didn't even have access to an Air Force thermal vacuum chamber. We probably would have known. We probably would take us 4 times to go through. But at 100,000 feet, the amount of heat that I generate in my body is almost exactly the same as what's conducted. I could have stayed there for a really long time and not need any supplemental heat at all. So it was a system that we over-designed, like way over-designed, that we didn't in practice, we didn't need anywhere near the capabilities that we thought we did. But anyway, I will tell you though that when you're in a freezer with liquid nitrogen, it's cold, like really cold. So I did learn that pretty quickly.
Awesome. Do we have any more questions? All right. I actually had one question. So what did you exactly do up there? Was it just to break like the world record, or did you guys do some science up there? What was the whole deal?
Well, science was really no one had ever built a self-contained system for surviving in the stratosphere. The science and the technology was really not about doing experiments while I was up there, but actually proving that it is possible to be able to build a system that does keep you self-contained. We learned a lot along the way. We learned a lot about oxygen systems. We learned a lot about suit architecture. Because we were so different than anybody else, like Felix uses a heated face mask and a fast oxygen delivery. So we learned a lot about those systems. We learned a lot about spin resistant systems. We learned a lot about spacesuit durability. These NASA was treating these things like with kid gloves that something would break, and you saw what I did to that suit multiple times. There's every landing was like that, and the suits are incredibly durable. So we learned a lot about suits. I learned a lot about, physiology. And so there was a ton of things that we learned along the way, but we didn't take up any specific experiments to do that. But if we did it again, I'm not doing it again. I'm actually working on, believe it or not, I'm working on autonomous deep sea exploration. Not with me doing it, but building robots that can actually explore the oceans, because I think that's a really cool problem. And um, but if we did it again, we had 100 things we would change. There's 100 things in that system that we thought we could do better if we had another shot at it. So someday somebody else is going to do it. Someday they're going to improve those systems, make them a lot lighter, easier, cheaper. So there's a lot of room for innovation still.
Awesome. All right. I think that's it for the questions. So once again, thank you, Mr. Eustace, for coming and giving this talk. I think we all enjoyed it. It was really, it was amazing.
Great.
So thank you so much for that. And yeah, guess we'll see you next time.
Okay, well, great. Thank you. Thank you for inviting me. Good luck in your careers in aerospace if you decide to go into that. And I hope to see you again soon. Okay.
Awesome.
Bye-bye.
All right. Thank you. Bye.
Bye.